Hi, this is Craig Stocks here for Utah Desert Remote Observatories. You can find us online at utahdesertremote.com. And today we're going to talk all about color, and particularly how it relates to astrophotography. We are going to get into the weeds a little bit and get into some of the details, but at the end we're going to circle back and I'll show you how to put some of this newfound knowledge to practical use. So let's start by talking about color. And of course in astrophotos we have color. Sometimes we have kind of natural, sometimes called RGB color or just natural color, something captured with the color camera. Frequently we also have color that was created from narrowband data, where we assign different colors to the different elements in order to create a color image that tells us more than just what the object looks like. It also tells us what it's made of. So where does that color come from? Well, we know that digital sensors use red, green, and blue photosites. And I'm sure you've heard the term RGB color. I just used it a few seconds ago. And that just comes from red, green, and blue. Our color cameras have red, green, and blue sensors that pick up red light, green light, and blue light, just like our eyes have color cells that pick up specifically red, green, and blue light. So the camera sensors really modeled after the color sensors in our eyes. If we look at the photographer's color wheel, and depending on what kind of artist you are, you may have seen different filter wheels or color wheels, but in general we have red, magenta, blue, cyan, green, yellow. Those 6 colors. Of the 3, red, blue, and green are considered primary colors, and then in between red and blue is magenta. Magenta is made from red and blue, cyan is made from blue and green, and yellow is made from green and red. Pretty straightforward. If we start with red, green, and blue, in terms of color, white is all of the colors, or gray would be equal amounts of all colors. Black is no color. So if we start with red, green, and blue and we combine those in equal amounts, the result of combining red, green, and blue is white, or a neutral color with no color to it. So think of red plus green plus blue equals white. Your monitor, your phone all have red, green, and blue pixels that light up and shine with red, green, and blue, corresponding to the red, green, and blue values at each pixel in the image it's displaying. And if all 3 are illuminated, what you see is white. If none of the pixels are illuminated, then what you see is black. When you print, though, you're printing onto a piece of white paper, so what you're printing on is already white. So we can't combine red, green, and blue ink and get white on a white piece of paper, because that's adding color to the paper. So actually your printer will use cyan, magenta, yellow, and then probably black, because the color combination usually isn't perfect. And this is called additive color, but the combination of cyan, magenta, and yellow combined together give you black instead of white. So that's why when you're printing with ink onto white paper, you use cyan, magenta, yellow, and black inks. When you're displaying light on a monitor or a TV or an iPhone, you're using red, green, and blue, and red, green, and blue combine to make white. In the absence of any of those being turned on, what you see is black. So additive and subtractive color. Cameras, of course, come in 2 different varieties. You can get a camera with a color sensor or a camera with a monochrome sensor. Now, the sensor's really the same. What's different is there's a color filter array on the color camera, and it's literally an array. A monochrome camera does not have a color filter array. Now, what that color filter array looks like, and it's usually arranged in a what's called a Bayer matrix, Each photo site has a filter in front of it so that it will pick up only one of the three colors. So each pixel on the camera will read just red light, just green light, or just blue light. And what you wind up with is actually a mosaic of reds, greens, and blues. And typically there's twice as many green as there are red and blue. So one row would be red, green, red, green, red, green. The next row would be green, blue, green, blue, green, blue. And so your raw file actually has 4 color channels, a red, a blue, and 2 green. And that's why you might have to enter the color filter array mosaic pattern or CFA pattern to tell the computer what order these colors are stored in. A very common one is RGB. When you demosaic an image in, whether you're doing it with a raw converter or in PixInsight, what it's doing is looking at each one of these locations and looking at the neighboring pixels. So for instance, if it looks at this green pixel, it knows that's the amount of green at this location, but it doesn't know how much red or how much blue. So what it does is it looks at the neighboring red pixels and the neighboring blue pixels, and it estimates how much green, red, and blue should be at each one of these photo sites. And it does that for every pixel in the image. So after demosaicing, you change this mosaic of reds, greens, and blues into an RGB image that has red, green, and blue values for each pixel. And now you have a full color image. And that, it's combining, for instance, the red, the green, and the blue all into one red, green, blue image. And any individual pixel is now defined by its red amount, its green amount, and its blue amount. So in this example, this pixel has a red value of 141, a green of 100, and a blue of 57. The problem is that doesn't completely describe the color of the pixel. That just describes the current values that it has. We need a frame of reference to know what that means. By themselves, they don't tell you anything. So consider this example. If someone asks, what's the temperature outside? And the answer is 20 degrees. You still don't know what the temperature is. You don't know if that's warm or cold because you don't know if it's being measured in Fahrenheit or Celsius. And it makes quite a difference because 20 degrees Fahrenheit is cold, 20 degrees Celsius is warm, around 68 degrees Fahrenheit. So you need that frame of reference or a measurement scale to interpret what 20 means. And the same is true with color. RGB values by themselves are meaningless without a frame of reference. And the frame of reference is called a color space. And what the color space does is tell us how those individual values relate to known defined colors or standard colors. So if I tell you that this particular pixel has these RGB values in the sRGB color space, now I know exactly what color that is because I know how to translate from any color space to any other color space, and I know what this triad of 141, 100, 57 in the sRGB color space, I know exactly what color, what tone, what hue, what brightness that pixel should be. So now it's completely defined. So the world overall contains lots of colors. In fact, it contains colors that we can't see: infrared, ultraviolet, X-ray, gamma rays, and so forth. Those are all types of light. It's just that our eyes can only see a fairly narrow range of visible colors called the visible spectrum. Monitors and printers can display fewer colors than we can see. So you're able to see colors that your monitor can't display, and certainly that your printer can't print. A colored space defines, among other things, the range of colors that are available within that universe of colors. The visible spectrum is usually defined in an LAB color space, in something like a CIE LAB. You may have seen that referenced somewhere. And sometimes they even specify D50 as the illuminant. That then, in most situations, the CIE LAB D50 is kind of the standard color that everything else works from. Color gamut, you may hear people use the term out of gamut. The color gamut is just the range of colors that can be displayed. And a color that is more intense or a hue that's outside of that world would be considered out of gamut. Now, the most common RGB color spaces are sRGB, and I'm going to tell you that that's the one you should be using, pretty much all the time to keep yourself out of trouble. Adobe RGB is a larger color space. It can handle more colors, more intense saturations. If you have a good high-end inkjet printer or a very good monitor, and generally that's going to be one that's well over $1,000, that can display the entire Adobe RGB 1998 color space, then that might be a good match for you. Profoto RGB is a very large color space. It even goes beyond what we can see in some cases. And it certainly is beyond what can be displayed, what can be printed. You might be tempted to think, well, that's the one I should be using because it contains all the colors. The problem is it contains colors that you can't see, that your monitor can't display, your printer can't print. And when you display something or print something, something has to give, and it's going to start mushing colors around to try to make them fit whatever your monitor or your printer can handle. And it just leads to problems down the road. So overall, vast majority of people, I suggest you just use sRGB. If you have a mirrorless or an SLR camera, set it to use sRGB. In PixInsight, if you go to Edit, Color Preferences, Color Management Setup, you have the option of choosing your RGB default profile, and I have that set to sRGB. So when I'm converting images to RGB, it's using the sRGB color space to set the values. For grayscale images, I use an Epson Gray Gamma 2.2, and that's a good match to what Photoshop is expecting when it converts from grayscale to an RGB color. If you have a monitor profiling system, then you probably have a device profile specific for your monitor. And in my case, I'm using this specific profile that was created with a color measurement tool, and it specifically profiles this monitor so that the monitor's displaying accurate colors. Most people don't have that. If you're in the Mac world, you probably don't need to worry about it too much. It's a little bit more of an issue in the Windows world where colors can be a little bit more all over the place. But most monitors, especially the newer monitors, are very good. If anything, though, they tend to be a little bit too blue and too bright. Brightness can be a real problem. Now, generally, after you change these, you'll have to click the solid circle to actually apply these settings. So let's hop back over here. In terms of color spaces, I said Profoto is the largest, but you can still think of it as having values from 0 to 255. It's just that 255 is defined to be a more intense color red, for instance, than in Adobe RGB. That same value is less intense, and in sRGB it would be even less intense. sRGB is really a good match for monitors. Online usage usually assumes sRGB if it doesn't know. When you create a JPEG, you have the option of either tagging it with the color space or leaving it untagged. I encourage you to choose the option to tag it with the color space so that any future user knows what color space the values in that JPEG are supposed to be interpreted. Online printing services usually assume sRGB, and this one in particular can get you in trouble because some of the less sophisticated printing services will just assume it's sRGB, and if you send them something that isn't, you're going to get really weird colors. Facebook is smart enough, it converts everything to its own version of sRGB. So when you upload an image, it actually converts it intelligently, and then everything on Facebook is in a Facebook sRGB profile. So just as some examples, the same RGB values, here 67, 96, 169, yields different colors in different color spaces. And that's why it can get you in trouble, because if you are trying to print this color and you send it to the printer with a Profoto RGB color space image, and they assume it's sRGB, then you're going to get this color instead of this color. Conversely, the same color, the same blue color, for instance, has different RGB values in different color spaces. So this is probably a good time to hop out of this presentation, and let's hop into Photoshop and look at some examples. So I talked about red, green, and blue as being kind of the foundation for color images. And that's because Photoshop is using the RGB color model, where it defines images as red, green, and blue. And just as an example, if we look at this image. So this is a portion of the Orion Nebula, and you can see in the layers palette I have the blue on top, and then the green, and then the red. So this was captured with a monochrome camera using red, green, and blue sensors, or red, green, and blue filters, I should say, monochrome sensor. If I want to turn this into a color image, one trick I can use, or one technique I can use, since this is an RGB image, and I can verify that by going to image mode, and I can see that RGB is selected. That means that I have, when I look at the channels, I have red, green, and blue channels, although for this particular layer, they're all going to be the same, because this is just the luminosity captured through a red filter. So if I go to this red layer and if I want to make this layer be just red, I can double click to the right of the layer name, and that will bring up the blending options in the layer style dialog. And under the blending options, you'll see channels are listed here: red, green, and blue. Since this layer is red, if I turn off green and blue, now all I'm getting is red. So I've now put the red data into the red channel. And if I do the same thing with the green, if I double click to the right of the layer name, since this is green, I would turn off red and blue. And now I have red and green. And let's just do the same with the blue. Double click. I'll turn off red and green since this is the blue information. And now we have a full color image. So that's just demonstrating how red, green, and blue are assigned into the red, green, and blue channels. Those channels combine to make a color image. If we look at this one, we have red, green, and blue. And same way, if I double click, this is an RGB image. So if I turn off the red, watch what happens to the red triangle or red rectangle. We no longer have any red in the image. That rectangle was pure red, so it just disappeared. And everything else, for instance, the white letters, when you take away red, what's left is green and blue, so they become cyan. And we can still see the green and blue rectangles. And in fact, if I turn the red on and off, you'll see the rectangles themselves don't change because they don't have any red. They're just green and blue. Likewise, if I turn off the green, turn off the blue. So that's just kind of demonstrating these are pure red, green, and blue. If I look at some copies of these red, green, and blue triangles, and if I move these around, so if I move this red, I keep saying triangles, they're rectangles. If I move this red over the green, you see that we have red and green, and where they overlap, we have yellow. And if you remember the color wheel, red and green combined make yellow. If I move the blue, blue and green make cyan. And where these combine may be a little bit hard to see, but where all three are combined, it's neutral gray because we have equal amounts of red, green, and blue. And I just arbitrarily defined these at 50% brightness. So that's a 50% illuminated gray patch that we're seeing in the center. RGB is one color model or color mode. There are others. If we look under image mode, what's checked right now is RGB color, but you can see there's also CMYK, LAB, and multi-channel. We're not going to talk about multi-channel. That's kind of a specialized color model that would be used by graphic artists, like if you're silk screening t-shirts or something. But other than RGB, another option would be CMYK. We talked about this is how your printer prints. It has cyan, magenta, yellow, and black inks. And if we convert an image to CMYK, we no longer have red, green, and blue channels. We have cyan, magenta, yellow, and black channels. Another very common, and I have kind of alluded to this earlier, is the LAB color space. And this one is kind of strange, but it tends to be the one that's the most universal for color processing. In fact, most of your image processing programs probably under the hood are probably using an LAB color space and color model. In the LAB color model, we have a luminance channel, that's the L channel, and it goes from black to white. And in terms of Photoshop values, it would be from 0 to 100. 100 would be pure white, 0 would be pure black. The A channel goes from cyan to magenta. The B channel goes from blue to yellow. If you use Lightroom, you'll notice, in fact, you'll see it in a lot of color processing programs, you'll see temperature and tint sliders. The temperature slider is really the B channel, that's the blue and yellow, and the tint slider would be the A channel. So what you're really doing is adjusting the A and B channel brightness or balance in a LAB image in order to color balance that image. So just like before, if I turn off red, green, and blue, we saw the individuals. Let's do something fun here. To start with, let's flatten this image. So I'm going to select Layer, Flatten Image. And I did that so that I can change my color mode from RGB, and this is currently still in RGB. You can see I've got red, green, and blue channels. Let's change the color mode from RGB to LAB color. Now if I look at the channels, you can see that I've got a lightness channel, and that's only showing lightness. It's not showing color at all. You can see that we still see the gradient in the L channel. The A channel, though, had color difference from side to side, but no difference in luminance. Likewise, the B channel had different color, but no difference in luminance. If we look at the CMYK, or even the red, green, and blue, you can see that cyan is a brighter color than magenta, and yellow is an even brighter color than magenta and cyan. And that's generally true. Blue would be considered a dark color, red's kind of a medium color, green is a kind of a light color, yellow's a very light color. So, for instance, if you increase yellow saturation, you're also increasing its brightness. If I look at the A channel, and remember this is the channel that goes from cyan to magenta, we can see the cyan changing values, but everything else is gray. Same way with the B. Let's come back here to the LAB version. So now we have all the colors turned on. If I do the same thing of going to the layer style dialog, instead of RGB sliders, now we see LAB checkboxes. And just like before, if I turn off the L channel, the luminosity, all I see is color. So this is showing the color of each one of those boxes, but no luminosity. And the default luminosity of 0 would be or 50% would be the neutral gray. That's the background. That's why it's showing as medium gray. If we look at just the A channel, you'll notice that this A gradient changed, and now it's just gray because we're not including any color information along the A channel. But you'll notice the B channel doesn't change. And likewise, if I turn the B channel off and on, the color in the B channel gradient goes away, but the A channel doesn't change. So we have completely separated the A and the B channels, color channels, where A is from cyan to magenta and B is blue to yellow. That's all interesting. How can we put this to use? Well, one of the things that you generally want to do in an image is have kind of consistent, uniform color saturation. You don't want one color to be more saturated than another color. You want them to be somewhat balanced. In a landscape image, if you increase the color saturation for, let's say, a field of flowers in the foreground, you run the risk of the sky getting too blue and too intense. So in a situation like that, you might want to decrease the blue saturation in order to keep the color saturation balanced. You might even want to decrease the blue saturation slightly more so that leaves the perception of the foreground being more saturated relative to what we expect a blue sky to look like. So let's look at a color image of an astronomical target, and let's say I want to really tinker with the color saturation here. In particular, I want to play with the yellow saturation, the blues, the reds. We can use the hue saturation adjustment layer, but let's explore a different way of doing it that sometimes yields good results. So to do that, I'm going to make a copy of this whole image. I'm just going to go to Image, Duplicate, and I'm just going to create a duplicate image. This is one of the rare instances when I would duplicate an image. And I don't want to affect the stars, so I'm going to turn off the stars layer. And then I'm just going to flatten everything else. And I'm flattening the image because changing color models will sometimes create unexpected changes in colors. And so this is, kind of baking everything in, so when I do the conversion, everything's going to stay the same color. So this is an RGB color image, and we can see that in the title tab. It says it's a RGB/16, so that's telling me it's an RGB color model, 16-bit color depth. If I come over to Image Mode, LAB, and switch this to LAB color, everything looks the same. Colors are all the same. But now, remember, if I look at the channels, I don't have red, green, and blue. I have lightness A and B. If I add a levels adjustment layer, and sometimes you would target, in an adjustment layer, you might target the reds, greens, and blues. Here, if I look at the channel drop down, I have lightness A and B. So this gives us the ability to separate color from brightness. And let's choose the A channel, for instance. And remember, this is magenta or cyan magenta. So the left side is cyan, the right side is magenta. And it's a very different looking histogram, that it's more or less centered. And we've got sliders at 0 and 255. And remember, this is the, it looks like it's grayscale, but it's actually representing cyan and magenta colors. If I move these endpoint sliders in, what I'm doing is increasing the intensity of that color. So if I move this left slider in, I'm actually going to increase the cyan saturation without affecting other saturations. If I move the red slider, the red side in, it's going to increase the red saturation without affecting any of the other colors. So I might find I might say, well, this is actually a better cyan magenta color saturation balance. If I go to the B channel, which is blue yellow, and do the same thing, as I move this slider in, I'm adding intensity to the blues or adding intensity to the yellows. I don't want to get the yellows very saturated, so I don't want to push that very far. I want to be careful with the blues because it starts to make the black background blue. The A channel, though, really helps me extend that cyan magenta color saturation. And if I just turn this adjustment layer off and on, it changed the color balance a little bit, but it also changed the saturation quite a bit. So how do I put this back into my base image? Well, this is an LAB color space document, but one trick you can do, if I select both layers, the background as well as this adjustment layer, right-click and convert to a smart object, that's going to encapsulate this LAB document into a smart object. And I can now move this smart object back over to my base image. And I want to put it right, I'll put it above my global adjustments but below the stars. So it will, when I drag it over, it will land right above what's currently selected. So I'll come back to my LAB image, select the Move tool, and then I'm going to just click and drag to drag it up to the tab for the other document. Keep holding the mouse button down, drag back into the image. I want to hold the Shift key to tell Photoshop to place this in the same location, and then let go of everything. And there is our LAB color space document now embedded in an RGB image. And we can turn the stars off and on. If I turn the stars off, you'll see that the document looks the same, whether we look at the LAB document or the RGB document. And if I turn that layer off, that's the change that we made. And I can turn the stars back on now. And if I save this, it will save it, replacing the existing document with this new and hopefully improved document. So that's a technique you can use to, it's kind of a different way of looking at color saturation, and maybe it's just me, but I find frequently I'm able to find a better color saturation balance by using the LAB color mode than I am in RGB using just the hue saturation adjustment layers. It does do a very nice job adjusting the colors, and you can even find situations where it will do a significantly better job than the standard hue saturation adjustment layer. So I apologize for getting so far down into the weeds, but I do hope you found this useful. If you have any questions, drop those in the comments down below. And as always, I hope you have a great day today and an even better night tonight under a clear, dark sky. Thanks.